Okay, guys, grow the farm up. We're going to have just a brief discussion here. We kind of opened a box of worms the other day on the Pharmacy Seeds Network, and I've done a couple of interviews since then and talked with a number of people in the basically nutrition based world and looking at not just genome editing for plants, but also gene editing. There's a big difference between genome editing and gene editing. I need to be careful and make sure I get my terminology correct here. But there's a couple of things that we wanted to discuss. I'm going to steal just a couple of clips off of this video here. Just a couple. There's my remote. Okay. CRISPR. My basic question to this is, a couple of channels that I interact with are into the all natural, very much all natural, and nothing wrong with that. In fact, really, I've come across channels like that and many different opinions, and my attitude towards the future of our food supply is I think the consumer wins, and the consumer should tell us what they want. That doesn't mean the consumer needs a bachelor's or MD in plant pathology or soil science or anything like that. But I think CRISPR represents some really interesting opportunities. Now, before we jump into it, I want to just steal a couple of slides from this, and let's listen to him for just a minute.
So here's a really simple cartoon to explain what gene editing looks like and how does it compare to traditional breeding. So in the middle is looking at traditional selection breeding. And the example that I have here is a tomato plant. If you take a tomato plant and you sequence its genome and look at all of the different base pairs that make up its DNA, and then you grew it up to a full plant and you collected a single seed off of that plant, you put it in the ground and you grew it up again. If you sequence the genome of this progeny of that original plant, you would actually find tens of modifications in the genome. Changes in the DNA code happen over time. That is the basis for evolution, and it's what gives us all of the natural diversity that we have. That's what.
Extremely true. Anytime you have the offspring, as he uses the term progeny, offspring of any living being, the genetic code is slightly altered. As he says, it's why no two human beings look alike. It's why no two plants look exactly alike. It's why even, I forget what they are, paternal or fraternal twins can not look exactly alike. And so genetic mutation is a natural process. I just wanted to cut in and mention that.
All plants don't look the same. It's why all people don't look the same. Breeders over the years have taken advantage of this change over time and the natural diversity that's there to really select plants that are different. The problem with this process is that it's slow and it's completely random. You have to wait for those changes to pop up that you're looking for. At one point, scientists created some different ways that they can increase this rate of change of the DNA code. This is called mutation breeding. Examples here are when they can treat it with particular chemicals or UV radiation to create thousands of random mutations across the genome. Again, this is very imprecise, and you don't get to choose where these changes occur.
Essentially GMOs.
And you get thousands of changes. So many times you do get that phenotype or the change in the plant characteristic that you're looking for, but along
with it, you change a whole bunch of other stuff that's not good.
With it comes a lot of baggage, so things that you didn't necessarily like. So you may have been looking for an orange tomato, and what you ended up with is.
And lastly, you have CRISPR gene editing, which is one precise modification. Very, very interesting. I want to steal this slide
that really came up in the 1930s when scientists discovered different ways that they could change.
We're gonna pause you. Okay, and this will probably jump on me, but 1930s we essentially began to naturally breed, hybridize things like hybrid corn. The 80s, that was the beginning of things like Starlink and Roundup. The 90s, that was GMOs, things like BT, Bacillus thuringiensis. Uh, 2011 and 12 is an interesting. Talons was the first kind of version of CRISPR, CRISPR-Cas9, which was the absolute breakthrough that we're going to discuss here in this video shortly. And then 15, 16, we've got CRISPR CPF1 and CRISPR CMS1 and a number of other things. Okay, the first thing I want to talk about, let's just dive into CRISPR briefly here. Okay, CRISPR, CRISPR, stands for Clustered Regularly Interspaced Short Palindromic Repeats, which allows for the manipulation of human, plant, and animal DNA and has been praised for its potential to treat cancer, remove inheritable diseases, and improve agricultural production. CRISPR has also been criticized as it can be applied in the germline editing process, which may lead to designer babies or parents hand selecting their child's physical or intellectual traits. Countries will have to delineate between permissible uses of CRISPR and uses that are considered immoral in their communities, although the agreement on trade-related aspects of intellectual property rights sets minimum standards and la-di-da-di-da. I don't want to bore you with just pages and pages of scientific babble here, but the thing about CRISPR is the way that it works is you're putting a nuclei into a gene. It's essentially a gene editing right here.
Nuclease. So this is the protein that physically cuts the DNA.
And pause. Okay. So the thing that's neat about CRISPR is the intellectual property laws that don't come along with it. Okay, that's the great thing about it, is that companies can own the nuclei in the nucleus, and they can create their Cas9, their CS159s. They can create all different types of what you would call pre-purchased or pre-laid out gene edits, but they cannot own the actual genome of any living being, while they can. And the patent laws on CRISPR they are a moving target, to say the least, man. To say the very least. I'm looking for the page here. Okay. Created. Yeah, I think I jumped around, but we don't care. We don't care, do we? Okay, again, CRISPR, or Clustered Regularly Interspaced Short Palindromic Repeats, allows for the editing of DNA. I'm not repeating myself. I'm just, I am repeating myself, but this technology has been likened to the find and replace function of a word processor, as CRISPR technology can identify problematic or disease-causing portions of an individual's genetic code and replace or repair them. Although gene editing is not a new concept, CRISPR provides a more efficient, accurate, and cost-effective solution. Understanding the function of DNA and RNA are essential to the understanding of CRISPR technologies. DNA, which stores genetic information, has the ability to control cells through a protein synthesis process, otherwise known as gene expression. Complementary RNA strands are created for the purpose of transferring genetic code information from the nucleus to the ribosome in order to create proteins. Thus, the DNA can transmit genetic code information needed for protein creation while remaining safely in the nucleus. CRISPR was adapted from a naturally occurring genome editing system in the bacteria and in nature as such, that the bacteria captures snippets of DNA from invading viruses and uses them to create DNA segments known as CRISPR arrays. The bacteria can remember certain viruses. That's what these nucleuses that all these companies are attempting to create right now and patent and sell, okay? But they're not owning the genome of any living cell or organism or being or plant or human. They're owning the bacteria, okay, in the nuclei. All right, and this bacteria can use an enzyme to cut the virus. DNA researchers were able to modify RNA to include a guide sequence that targets specific DNA sequences. The modified RNA attaches to the enzyme and can locate and cut the DNA in the same manner as it occurs in nature. Researchers then use the cell's own DNA repair machinery to add or delete pieces of genetic material to make changes to the DNA by replacing an existing segment with a customized DNA sequence. And that's essentially the big difference between GMOs and CRISPR. People hear, oh, GMOs, CRISPR must just be an extension of that. Not, it couldn't be further from the truth. I want to go back here and let's see how far and how, let's see just how horrible we can.
To your starting material to identify just that.
Apparently it takes a minute. I don't really like his explanation of mutation breeding and selection breeding. They're essentially the same thing. What he's telling you is that we used to take 1,000 seeds, throw them out there, and we used to have to weed out 90% of the plants because only 10% of the plants express the characteristics that we want. And then he basically sums it up and says, and scientists just came up with ways to change that to where we throw 100 plants out there, plant them, and we only need to weed out 20 to 30 to 40% of the plants instead of 90, which is much quicker, but still takes a long time. But a lot of other bad stuff comes along with it. And then Talons and Cas9 comes along, and oh my gosh, in one shot, we can change it. So again, I'm not arguing for or against CRISPR. I'm asking you, can we put CRISPR in the toolbox as plant breeders in the next evolution of the food cycle? And that's a question I'm asking you, the consumers. Okay, so now let's look at the potential of CRISPR applications, all right? Curing diseases. As stated previously, CRISPR technology has the ability to edit plant, animal, and human genes. The most promising CRISPR applications in humans is the editing of genes in a way that fights diseases or disease. Researchers have conducted studies on mice and have corrected mutations that cause sickle cell anemia, muscular dystrophy, cystic fibrosis, things like this. Clinical trials will soon be conducted for a technique that uses CRISPR technology to cure a rare form of blindness. Further, CRISPR represents possibilities to edit away inheritable diseases and congenital conditions, which is that, as we've discussed, utilizing, disrupting endocrines and how you can pass that on to the next generation. The food that we've been eating for the last 20 years, if it's not healthy and if it's actually changing our genome because of all of this bad crap we threw in it to make our GMOs work because we just didn't have the technology there. Is this CRISPR the technology that can come back, wipe all that out, and essentially bring us back, start over, and almost start fresh? It's an interesting and different perspective. I know many people will have different attitudes and opinions on it, and that's what we're here to ask for. But I'm going to ask you a very interesting question at the end of this video. We'll see what you think. Okay, CRISPR can also be applied to plants to accomplish industrial tasks. For example, Chinese scientists are using the technology to delete genes in wheat strains in order to make the strains more resistant to certain pests. In 2017, Japanese researchers used CRISPR to change the color of a flower from violet to white by editing a single gene in a very simple Cas9 experiment. Nothing, too earth-shattering there, but drug developers are also excited about the possibilities presented by CRISPR technology because CRISPR can modify hundreds of thousands of genes at one time. Think about that for a second. One nuclei. researchers can test for possible causes of illness with greater ease. For example, cancer cells often need to be targeted by multiple drugs, and their susceptibility may vary from patient to patient. CRISPR will permit more rapid systematic testing and modeling of how cancers develop and how they can be defeated. It talks about transplantation. You know, it's long been I don't want to say a dream of the medical world, but to transplant pig parts into humans. But because of some of the bacteria found in pig DNA, the human and the pig parts don't actually go together. I look at it more towards if you get a liver transplant or you're fortunate enough or unfortunate enough to need or get a heart transplant, using CRISPR, the chances that your body will not reject that transplant are like 100% if you use it properly. Okay, now let's look at germline cell editing. Okay, although the discourse regarding CRISPR has been largely positive due to the potential problems it may solve, there are many who are concerned about its potential uses. Thus far, CRISPR editing techniques are limited to somatic cells. This is very important, which are cells other than egg and sperm cells. We talked about passing along these gene edits to the next generation, just like we had issues through our GMOs of selective breeding here, okay? Right, so it's limited to somatic cells, which are cells other than egg and sperm cells. These changes affect only certain tissues and are not passed on from one generation to the next. That is huge. This the technology that can wipe out the last 40 years, 30 years, 20 years of horrible
DNA code through mutagenesis.
And we'll pause there. Is this the technology that can literally wipe the slate clean, going all the way back to about here? That's where we need to wipe the slate clean to be quite honest with you. Okay, but altering egg cells, sperm cells, or genes in an embryo can result in such changes being passed down through generations and is known as germline editing or genome editing. Okay, it's very important to get your nomenclatures and your terminology correct. This is not genome editing. This is gene editing, okay? Genome editing is, it says right on there, it's capable of genome editing. What I'm telling you is that right now, it's only legal to use on somatic cells that are not genome editing, okay? This is, let me find my spot here again, where genes, embryos, it can result in such changes being passed down through generations and is known as germline editing or genome editing. Germline and genome editing has been controversial for many years. It's been controversial since GMOs came out, as concerns have been expressed over eugenics and designer babies. These are some different concerns than we would probably pose in our discussion about the future of food, but this is very real, created to maximize intelligence or attractiveness. Would you like to choose the color of your kid's eyes? Would you like to attempt to edit the genes to make them tall, short, brown hair, blonde hair? There's a lot of different things that can be done here. There's an example here of a Chinese scientist that attempted to use CRISPR technology to repair a gene for a blood disorder in non-viable embryos. I believe this was a couple of years ago. It states it in here. The Chinese scientist announced that he'd use CRISPR to alter genes in embryos that would make the babies resistant to HIV. The embryos were later placed into a womb carrier, if you will, just to simplify it, came through and were born, and now they're resistant to HIV. So the question that I have for you guys, the good thing that comes with CRISPR is it's all of the intellectual property laws that don't come with GMOs. I mean, the ridiculous patent system, and there's a race for patents right now, but right now, really all you can do is patent the nuclei. That's all you can really do. And there's companies that are making all different kind of nuclei. So if I want to give this a minute
These
here to
two
load
components, they come
and pause you. Okay. So if I want to try to edit some guide RNA, if I need some guide RNA because I'm trying to edit some DNA, okay, I can go buy nucleus bacteria RNA from one of about 3,500 companies right now that are working on developing uh, their own RNA crosses. And as we said, it's CRISPR is basically like the word processor. You know, it scans across your screen and goes, nope, you misspelled that word. We need to respell. It's like the spell checker of gene editing. So the question that I'll ask you, and this video will get too long if we go into every last subject. Question that I'll ask you is, when I first looked at CRISPR, the first thought that came to my mind was when my kids were born. If the doctor came in and told me that one of my kids was going to be born with a great deformity or defect, and they could use CRISPR to fix that so that the child would be born without any defects, would you say yes or would you say no simply because you don't think that it's quote unquote an all natural process? Would you, in a sense, throw the baby out with the bathwater? If you had a family member that was suffering from a terminal disease such as cancer and CRISPR technology could help, would you say, no, I don't want you to use CRISPR technology simply because I don't think it's an all natural process? One, do we know enough about CRISPR to say it's not an all natural process? Because gene mutation is a very natural process. This might be the one piece of gene editing that is definitely worth looking into. And once we get it to the point where people are comfortable enough with it, we can turn it into genome editing, which will, that's one of the reasons the big GMO labs still exist today and we still use the selective breeding through GMOs, is that we do not have, it's not legal to use CRISPR Cas9s and CRISPR CS1s to do genome editing yet. It's only allowed to do it through the non, what they call, what's the name of that? Somewhere in here, I will find it. Okay, there we go. It is limited to what's called somatic cells. Sorry, it was on the tip of my tongue. I want to be careful with my terminology here, but limited to somatic cells. So currently, we're not utilizing CRISPR to edit, cells that are basically related to egg and sperm cells and those changes that may affect tissues that are passed on from generation to the next. We're only using CRISPR to be limited to the somatic cell research. But it is an interesting question to ask yourself. If you were really sitting there and put yourself in those shoes for a minute and say, look at today. CRISPR could be the solution to swine flu, to whatever that was, avian bird flu, obviously coronavirus. There's a lot of different things here. It's why I didn't just jump straight into plant breeding and CRISPR. CRISPR is being looked at as a wide, just expansive, almost just piece of research that's been uncovered, and it's been in the works for 5, 7, 8 years now. And I mean, it's been used widely and is being used more and more widely. And when you realize that, it can help cure some of these things, I understand people's concerns with it. I do. It's why I made this video. It's why I went on the Pharmacy Seeds Network, and I also went on a couple of other nutrition-based channels. Went on with the Food Cook channel and discussed nutrition and asked him, and he was very big, just like the Pharmacy Seeds Network was, and most of the people on the Pharmacy Seeds Network chat were very much about, you know, all natural. If it's not all natural, I don't touch it. And I was very happy to find that, you know, an open-minded set of people and an open-minded person running the channel. And I think that's because I approached them with a very open mind, saying, hey, I'm an independent plant breeder. The future of the food supply is, I guess you could say, somewhat at stake here. And as we look forward and reshape this and create a healthier, more nutrient dense food supply for everybody, can I put CRISPR in my toolbox? You know, let's get educated about it. Uh, Look it up for yourself. There's tons of data on Google. Read through, see what you can find out about it, and determine if it's good, bad. If you like it, don't like it, comment below. I'll link a couple videos to the bottom of this video so you guys can check it out. But anyway, that's just a quick CRISPR 101. Wanted to make a quick video about it. Don't even know how it turned out. I hope the phone's even recording, so I hope it was some decent information to give you guys and some food for thought. All right, guys, grow the farm up.